Okay, dear students, now we are going to start our new chapter, which is wave motion. Wave motion, basically what is wave? It is a mean of transferring energy and momentum from one point to another wave. We usually represent a wave like this, and it shows that it is transferring their energy from one point to another. Here, this shows this point is representing the crest of a wave, and this is representing the trough of a wave. Basically, the waves here, these are of two types, which are mechanical waves, and second is electromagnetic waves. The mechanical waves basically need the medium to travel, like sound wave are mechanical waves, medium to travel. But electromagnetic waves do not need material medium to travel. Okay, so basically we can say give the example of light waves. These are electromagnetic waves. In this chapter we will focus over the mechanical waves only, right? So in mechanical waves, basically they are of two types, further divided into two types, that is transverse waves, and second is longitudinal waves. Transverse waves are basically the waves which are represented like this. Here the particles are vibrating about their mean position. Okay, here they are executing simple harmonic motion about their mean position and in a direction perpendicular to the direction of motion. Now basically the direction of motion is in this direction, and they are oscillating the simple harmonic motion in the perpendicular direction. So such kind of waves are known as the transverse waves. For example, the movement of string of a guitar. Okay, in that case also, when you vibrate it, the string oscillate like up and down, and the oscillations move further. Second is the light waves all also, which are the electromagnetic waves. All the electromagnetic waves are basically the transverse in nature. Now second, in case of transverse waves, we have crest and trough, as I have already told. And in that case, the length of a wave, which is represented by this, is given by nu into v into t. Here lambda representing the wavelength, v is the velocity, and t is the time taken at an instant of time. Similarly, second is our longitudinal waves. Longitudinal waves are those waves in which vibrations takes place, but the body oscillates about their mean position in the direction of motion. So in this case, that waves are represented as like this is compression and rarefaction. Compression and rarefaction. So basically compressions are the region of the greater density and rarefactions are the region of lower density. Sound waves basically are the longitudinal waves, and this travel in the form of compressions and rarefactions. So compression, which is our regions of high density, and rarefactions, which are region of low density. And now let us talk about the wave function. Wave function means wave function is a function which is used to represent any wave. In the previous chapter, we have studied that simple harmonic functions are representing a sine and cosine wave. In this case also, we will use the same argument, but in this case, the argument of sine, basically we will write x into t, because here the wave is dependent on x and time also. Okay, means displacement and time also. So that is represented by r sine. Here there in that case we write sine omega t only, or omega t plus theta, phi, or phi minus phi. But in this case we will write r sine, right? This is 2 pi by lambda vt minus x plus phi naught. Here this component 2 pi by lambda vt minus x is basically representing omega t. We know that omega is equal to 2 pi by t. Okay, so if we open it up, this will be 2 pi by lambda by v, that will become t into t. Okay, so that comes out to be omega t, and minus x is taken for representing the displacement of the particle from its mean position. So in this case, we can represent the sine wave like this and cosine wave like this. Cos xt, r cos 2 pi by lambda Vt minus x plus phi naught. So this is the expression for the wave functions for a simple harmonic wave.